Okay. Well, yeah, well, thank you for the invitation again. So I hope you'll find this interesting. So, we start with, just so that it's super clear, what kind of ODEs I'm going to talk about. So I will only look at systems of ODEs. So we have n variables. Derivative of each variable is a function of time and the other variables. So I'm going to write the system once, and then it's going to be y prime equals f of yt, because it's more compact. And a small trick, which is quite obvious, is that I'm going to get rid of the time just by adding another variable, which is always possible. You just say derivative of time equals 1, and thus my ODEs will always be autonomous. And it's, in fact, doing this transformation is like almost for free, because sometimes what you do is that you assume different behavior for f for time and space variables, but here it's not going to be important. So because most of the time things will be either Lipschitz or just continuous. So it's not a problem. So in general, things will always be of this form. Initial condition, y prime equals f of y, where y is a vector value function, and f will always be at least continuous. Okay? So this is the kind of equation I want to look at. Now, for computability, I will need to say things about computability of real functions. So I'm going to assume you know classical computability, so Turing machines. So with Turing machines, you can work over words, integers, rational numbers. Rational numbers are just integers. So a function from rational numbers to rational numbers, being computable is completely unambiguous. Okay, whatever model you have, it's always the same thing. However, if you want to say that a function from real numbers to real numbers is computable, things are not so clear. So there are different models, and there are at least two big models that are completely different. So I want to mention both. The first is the BSS model, Bloom-Schutz-Smell model. Those are basically register machines that can store arbitrary real numbers in registers. And on top of that, you can compute arbitrary rational functions over real numbers at unit cost. So for example, you could write A equals pi, B equals E, C receives AB. This program has running time free. It takes 3 instructions, they're all unit cost. Okay, so this is the BSS model. And on top of that, you're allowed to do comparisons between real numbers. So you could say things like, is it true that C is less than, I don't know, 1? Okay. On the contrary, there's another model called computable analysis, where, here the idea is completely different. We don't want to be able to manipulate real numbers at unit cost because it's not realistic. So we represent real numbers as converging Cauchy sequences, and everything is done via approximations on rational numbers.
And so this first model, is it based on something actual, or is it just an...
It's the first model is purely theoretical. It's basically there because it has a nice theory. And you can relate Turing machines to this model. It's also much simpler because if you do complexity in this model, then you don't have to care about things like, oh, how much time does it take to multiply 2 integers? Well, the answer is 1. Okay? It's not realistic, but it's simpler. Okay? It's also very used in geometry complexity, because if you start caring about how you represent numbers, things get like so much more complicated. So this is simpler, but it's not realistic. And the second one is you care about all the details, so you do everything via approximations. And in particular, you cannot even compare to real numbers, because if you're given 2 real numbers and the only thing you know about them is give me arbitrary approximations, then you can never really be sure they're equal. If the first 1,000 digits are equal, there could still be a further digit that's different. So comparing 2 real numbers is not even decidable in general in this model. So it's completely different. In particular, in this model, any computable function is necessarily continuous. So those are like incomparable.
So, but how do you present converging Cauchy sequences? By recurrence or by infinite amount of
So if you want the details, it's represented by oracles. So an input, a real number, an input is an oracle, and you can ask the oracle, give me the input with 10 digits, or 100 digits, or 1,000 digits.
Okay.
And the output is basically, the machine itself is an oracle. If you ask the question, give me the result with 100 digits, then you can query the input oracle.
Mm-hmm.
So that's how it works.
Okay.
This model. And in this talk, I'm only going to use the second one because it's the more realistic one. The first one, you cannot really implement it. So I'm not going to care about it. But usually, if things are computable in the second one, they're obviously computable in the first, so it's not a problem. So what's the problem I'm trying to solve? Many people have tried to solve it. So we're going to assume f is continuous, and we have a C1 function y that satisfies the differential equation. So for simplicity, I'm always going to take the initial time and initial condition to be 0, because again, I can shift things, it doesn't matter. And what I want to do is find a program that, given t as an input and n an integer, compute a rational approximation of y of t for some norm. That could be the infinity norm. Okay, it's not very important. And t, for example, you could assume is rational number if you want.
Are these two n the same? Like n?
Yes, no, it's a different n, sorry. So let's rename this n is the dimension, okay, so.
Okay, good.
Yeah, okay.
So I see.
It's a more different n.
and the function f is represented also like as an oracle. So I can give input with some accuracy and then we'll get output.
Yeah, so their subtleties about how you represent f, maybe I will mention them as they go.
Okay.
But because if you just have an oracle, it's not quite enough. So for now, let's ignore this issue and then talk about it when it comes in. So what I've written in blue is basically the definition of why is computable. Okay, skipping some details. So my question is the solution computable? Where first of all, it's clear the solution exists, at least one solution exists, that's Peano's theorem. Because this f is continuous, so this equation has at least one solution if I is small enough. Okay. However, it could have several solutions. So the question is why computable is already imprecise. So we could say, is at least one solution computable? The answer is not necessarily yes. So it's an old result that you can build a continuous f computable such that it has many solutions and none of them is computable. So you cannot even hope for one of them to be computable because it's not always the case. So obviously this f is very artificial and complicated, but
how old is the result?
It's at least I think it's from the 60s, but I'm not sure.
Oh, 60, okay.
Yes, I think so. I think it was observed quite a long time ago. Yeah, unfortunately, if you know nothing about f except it's continuous, the situation is just hopeless. So, in general, we want to assume at least unicity of the solution. Otherwise, we run into this problem and we don't really know what to say. So, if f is computable and we assume the solution is unique, then things are manageable. The solution is always computable. So this is a pretty old result. If it's not trivial, because if you really just know that f is continuous, it's not clear how you compute a solution. Here you need to represent f with slightly more than an oracle. You need to know if you have f, like you have like this. If you give a value, you need to be able to compute arbitrary approximation, but you basically need to know some kind of local modulus of continuity. Because you know f is continuous, but if you don't know how it behaves, it's not enough. So you need to have some local constant, local modulus of continuity. So the oracle gives you both information. You need to know both things. Okay. But again, it's not super important detail. Now, one thing you may ask is, for now, I've just assumed that the solution exists over I. But one question you could say is, can I compute I? Can I compute the maximum interval of life, assuming the solution is unique, so it's well defined? And the answer is no. Surprisingly, the question, can you compute I, is undecidable. And you cannot even decide if I is unbounded or not. So you cannot decide if the solution explodes in finite time or exists at all time, even if f is very restricted, like a polynomial. So it's slightly scary. It means that in practice, you always want to assume that when you ask the program, give me y at time t, you want to assume t is in the interval of life, because you cannot decide whether the solution exists or not. Okay? So in practice, we work around this problem by always assuming things belong to the interval of life. Okay? And the way this result works is basically you can prove that you can simulate Turing machines by differential equations. And thus deciding whether a solution exists or not would be the same as deciding whether a certain Turing machine holds or not. And finally, there's another subtle issue at play here, which is quite important. If you just look at the second result, it says if f is computable, then y is computable. It doesn't tell you there's an algorithm that maps f to y. It could be, if you just know the second theorem, that there's a different algorithm for each f. And this is not the same as saying that from f you can compute y. So the answer is yes, actually, if you just know f, you can compute y. This whole map, this operator is computable. But this is a different result from the second one.
So the second one essentially proved like constructing an algorithm for each f.
It says for each f there's an algorithm, but
it's an existence proof.
It's an existence proof.
Okay.
But potentially this algorithm actually relies on doing things about f that you cannot compute. So it's a different theorem here that says, okay, now I know f. I know nothing about it except from this oracle, and this is, I want to compute y from f. So I lied a little bit. The second result does not take f as an oracle, in fact. It's an existence proof. This last result actually takes f as an oracle. So it's a subtle issue, but it's quite important, in fact.
Does it actually give an explicit algorithm?
Yes, the last one, it gives an explicit algorithm. But this algorithm is really horrible. It basically enumerates things and proves that at some point you're going to find something which works. So it's like, I know something exists, and I just search all things until I find it. So it's, even if you implemented it, you would run it on any example, you would never get a result. It's just too slow. It's a purely theoretical result.
Let's go back. Update.
Should I go back to the beginning?
Just a little bit quickly, maybe.
Okay, so just go back to the beginning quickly. So, as I said, I'm only going to look at system of ordinary differential equations. So, n variables y1 to yn. The derivative is a function of time and the function. For simplicity, I'm always getting rid of the time by introducing another variable. And thus, the systems are always autonomous. And those are always systems over these. Okay. Since I'm going to say things like the solution is computable, I need to explain what it means to compute over real numbers. So there are two different models to compute over real numbers. I mean, there are more, but the two big models are BSS and computable analysis. So BSS is a purely theoretical model where we assume we can deal with real numbers at unit cost. So we can write things like A equals pi, B equals E, C equals A times B, and at unit cost. And I can do comparison between numbers. So this is unrealistic, but it has a nice theory. In computable analysis, on the other hand, we don't assume we can really have access to real numbers. We just do everything via approximations. And in particular, we cannot even compare numbers. But the important feature of the model is that computability implies continuity. So
who came up with number two?
Number two, you could say it's Turing in some sense. Turing already thought about computability over real numbers, but he didn't come up with a really formal model. And then there were several models, but the one who you could say really wrote the formal model was Weierhosch. And then actually computable analysis take a different it tried not only to talk about computability over real numbers, but it tried to talk about computability over abstract things, like what does it mean to compute over a binary space? What does it mean to compute crazy abstract things? And it kind of lost its roots about real numbers. But initially, it was how you compute about real numbers. So, as I said, I'm only going to care about the second one, computable analysis. And important things to know. So the problem we're trying to solve is, given a differential equation, is the solution computable? And then we're going to see what is the complexity of computing the solution. So things to take, you should take care about. First of all, if there are several solutions, it's not clear any of them is computable, because there's a counterexample. A system where for computable f, none of the solutions is computable. If the solution is unique, then it's computable. So at least we know that.
Does it take pages and pages to describe this f?
Kind of. It's maybe 20 pages the total paper, but it's it's kind of fractal, as you can guess. This f is kind of fractal, and you have to deal with many details about how you build it. So it's complicated f. Yeah. There's this solo issue about computing the interval of life. So in general, unfortunately, we cannot even decide whether the interval of life, the maximum interval of life, is infinite or not. So we always have to assume the t's we give are in this interval of life.
And that's even true if f is quadratic.
Yeah, it's even true if f is polynomial. It's also true if f is quadratic. So it's really hard to work around this problem. You really have to assume the solution exists. I don't know any solution to this problem. And finally, there's this solo issue of the difference between knowing that if f is computable, then y is computable, and the fact that from f you can compute y. Those are two different things. The first just tells you that for every f, there's an algorithm to compute y, but this algorithm may be different for each f, and the fact that actually the operator that maps f to y is computable. So from f we compute y.
How long is the code?
Of this?
Yes.
Well, the paper is quite long. Actually, I think the code itself would be relatively short. It's basically enumerating sets of boxes and checking things are true with interval arithmetic. But then there's a lot of work about proving it's actually complete. So I think the hard part of the proof is proving that you enumerate objects and proving that it's really complete, that you eventually find something that works. But I haven't read the paper in a long time, so I don't remember. The name of the paper is something like the 10,000 monkeys approach to finding the solution. It's not a joke, it's really the name of the paper. And then it also works for differential inclusions, if you really want to know. You can also do differential inclusions like this. So you have f, which maps points to a set of points. And you do things like you assume y prime belongs to f of y. This is a differential inclusion. So you don't assume you know f, you just know, like for example, f of y could be a small ball, and you're looking for something that satisfies this equation.
What does it appear?
It's one way of modeling the fact that you don't know the equation. So for example, if your equation comes from physics, and you know there's uncertainty, then that's one way of doing it. It's a pretty obscure thing. I had never heard about it before reading this paper, so yeah. Okay, so this is all about computability. So far, if you try to implement any of those algorithms, it's going to be horrible, because anyway, if we don't know anything about f except it's computable, then we can spend most of the time just trying to compute f anyway. F could be arbitrarily complicated to compute. So just because of this, y could be arbitrarily hard to compute. So we need some assumption on f maybe to hope that y is easily computable. So this is complexity, and there are different approaches to complexity. And the first one, if you look in the literature, is what I would call the textbook approach, numerical analysis approach. And a typical textbook result looks like this. Usually you assume f is Lipschitz. It's already quite a strong assumption. Computable, obviously. And you assume the solution satisfies this. And for example, you would read this theorem. It would say, here's a method called the Runge-Kutta method. So you would have some code. Okay, it's actually quite simple to implement. And it would say this method has order 4. So what would that mean? It means that there's an algorithm that given a time t and a time step h, so you have to give h to the algorithm, that's a parameter, and the algorithm returns q, a rational number, such that the distance between q and the actual solution is less than big O of h to the 4. And furthermore, the runtime of the algorithm is big O of 1 over h to the 4. And then other things like maybe the method is astable or whatever. Okay, so this is typical result from textbook. Okay, so what does that mean? It means that when h is very small or tends to 0, then your method is correct. Okay, eventually q is going to converge to y of t. And usually this is going to be followed by benchmarks to show that the method is not only, it works, but it also it's practical. It works pretty fast on practical examples.
And so that just precisely what that big O means.
So that's the problem. The problem is if you just know that, you don't really know much. You know it works eventually, but you don't know much in practice because the accuracy of the results is this big O. It means, okay, there's a constant A such that the bound here is less than A times h to the 4, but the theorem doesn't give you A. So for any concrete h, the algorithm gives you something, you have no idea whether the result is correct or not. You don't even know the distance between this and the actual result. So it only works if you think the algorithm is going to work on this example for other reasons. Like maybe my algorithm always works on this example. Or you know the result and you can compare it to what you got, which defeats the purpose. And it's the same problem with complexity. There's a constant here hidden in the big O of 1 over h to the 4, and you don't know that constant. So for concrete h, you have no idea how long the algorithm is actually going to take. And on top of that, f being Lipschitz is a strong assumption, because for f polynomial, for example, there's no way f is going to be Lipschitz. So typically, this is only going to hold if you know, for example, that y belongs to a compact set, and then you only need f to be Lipschitz over this compact set. So in practice, if you just know this theorem, this is not really useful. In terms of complexity, it doesn't really tell you what's happening. Now, sometimes you actually have an explicit bound. For a simpler method, you can hope for a simpler bound. So let's look at a concrete example.
By the way, so I assume there are other methods, right?
Yeah. So I took Runge-Kutta method, but there are many methods.
Do they share this similar?
Many of them share this pattern, yes.
Are there any others that don't share this?
Yes, I will. Yeah, there are many others, but most numerical methods this follow this pattern. So yeah, but I will mention others. But I think it's important to understand this, even if it looks like a bit crazy, because it actually highlights a problem that's not specific to numerical analysis. It's also a problem in other approaches. So.
And how is such method used?
Well, that's a bit of a mystery to me. There are hundreds of papers on numerical analysis and methods like this, and they always want to be more efficient, but I don't know if they're actually used in practice, or at least if they're used, they don't care about correctness of the result. I don't know, it's a philosophical question. If you know your system is rather stable, you simulate it, and the result looks correct. I don't know, you simulate a plane, and your plane seems to have a good behavior, then you could think maybe my method was fine. If on the other hand it's fast, you could argue that's good enough. I don't know, that's a philosophical question. I don't want to answer it. So for me this is strange, because I care about correctness of the result. I don't care if the result is not correct, but if you don't care, That's your problem. It could be useful to get maybe a feeling about how the system behaves. Maybe if your simulation is accurate, maybe you can guess how the system behaves like this. Or as a heuristic, like you plot it on Maple and then maybe it tells you something. So here is another example, slightly more concrete. If you take a simpler method like Euler's method, which I'm going to explain later, then actually you can get a theorem like this. It tells you, okay, the actual error at the end of the method is this expression. So h times m over 2 to the k exponential kt minus 1. K is the Lipschitz constant of f. And m is this supremum over the interval of the second derivative of y. Okay, so this is good. That means now you can compute the error bound. And in particular, you see that this expression, if I is compact, then this supremum is well defined. So this is a big O of H. This is how you typically obtain results like the previous one. Okay, this is where this big O comes from. However, there's something a bit problematic with this bound, which is, first of all, you need to know K. So F has to be Lipschitz globally, which is a strong assumption, or F has to be Lipschitz over this set of points that Y is actually going to use. So Y is bounded. But since you don't know Y, you don't know which part of F you actually need, so computing this K might be non-trivial. For example, if you know that Y belongs to this rectangle of size L, but you don't know what is the size of this rectangle, then you cannot compute K. So you need to know Y to know this bound. But actually there's something a bit worse here, which is M itself depends on the second derivative of Y, but you don't know Y. So how can you know the second derivative of Y on top of that? This is Y could be bounded and its second derivative could be completely unbounded. So there's a chicken and egg problem where the constant in the accuracy bound depends on computing the solution itself. So unless you know something more about Y, there's no way this bound is really useful. You need to know more about Y to actually use this method.
How do such results get published?
Because you don't show the expression, you show the big O. I don't know, or maybe it's just in textbooks, which is scary for other reasons then. I really don't know. I don't know. I find this kind of results. The thing is, the methods themselves are quite interesting. It doesn't mean that because of this theorem, you could feel like maybe this is not serious math. But actually, the math that goes into these methods can be quite sophisticated. But just the way the results at the end are phrased makes no sense. Like this makes no sense. Now you could say, okay, this is, at least for compact domains, maybe if you know things about why this works, but there's another problem something that I've heard several times, which is the rescaling myth, which is what happens if I is unbounded, okay? And this is where it shows that this whole thing really breaks down. If I is unbounded, what could we do to compute y of t? Well, you could say this is easy. I just define another differential equation where I put my t inside so that the solution at time 1 is equal to what I'm looking for at time t. And then this satisfies a new differential equation, but now I only need to solve it over 0, 1, which is compact. Okay? And then you could say, oh, well, this is great. Now my algorithm has accuracy big O of h, and everything works. Except that now, basically, you've ignored all the interesting parameters of the problem. So what's the meaning of a complexity bound where all the interesting parameters of the problem have disappeared into a big O? This is really a strange thing. And this is obvious if you write explicitly the constant. The constant in the big O is some constant that depends on the Lipschitz constant, and this, for example, for Euler's method, it depends on the second derivative of z over this compact domain, but this compact domain is compact but depends on t. So in fact, everything depends on t in this equation. So it's really hiding most of the interesting things, and only care about this parameter h. But h, I would say, is the least interesting parameter of the problem, because that's the one the user has to guess. And that's the one that the user doesn't want to provide. If you solve a differential equation, you don't care about h. It's always going to be, oh, let's take 10 to the minus 4 and hope for the best. So this is not what you care about in practice. And on top of that, if you're solving over unbounded domain, then you really need to know that f is globally Lipschitz, otherwise this whole thing just doesn't make sense. So what I wanted to say with this is that those methods, they might be practical, but they tell us nothing about the actual complexity of the problem, despite what the theorem might, despite what the theorem says. It tells nothing really about it. So fortunately, it's not the only method. There's another approach, which is to admit this problem and say, okay, it doesn't matter. Let's take what we've just done, but on top of that, now, the algorithm is going to output some epsilon, which is the actual error bound. So now the algorithm not only computes the approximation, but it also computes an upper bound on the error it has. So this is more complicated because now you need to estimate the actual error you have, step by step. But it can be done in some cases. And the guarantee is that if h tends to 0, then epsilon tends to 0. So the algorithm is eventually correct. And for any given h, you can run the algorithm and see if the error you have is satisfying or not. Okay? But the problem is now, if you do this, you have no upper bound on the complexity. Like, it's pretty clear because of the theorems that we've seen at the beginning that there's no hope to have an explicit error bound based on h. And the way that works usually is you rely on interval arithmetic. So every time you do an operation, you keep a bound on what the result should be, and you accumulate those error bounds, and at the end you just see what you have. And this can be done for everything. So this is why you don't get error bound. You don't get complexity bounds with those methods. So that's one approach. It's correct, but it doesn't give complexity bounds. Now, if you're willing to give up any practical algorithms, then there are some theoretical results that are more of interest, at least maybe in this case. Here, the idea is, okay, we're not gonna claim we're doing anything practical. We just want to study what's the theoretical complexity of y depending on f. So if we know that f is computable, then we know that y is computable if it's unique, but y could be arbitrarily hard to compute. Okay. So you might say, well, let's make a strong assumption on f and see what happens on y. So for example, if f is polynomial time computable, so computable really quickly, polynomial time. I will not say what it means for f real to be polynomial time computable, but okay, it's computable easily, let's say. Then you might think, well, maybe the solution cannot be that hard. In fact, it's not true. You can find examples where f is very simple and y is still very hard to compute, arbitrarily hard to compute. Like for any complexity bound, you can find an example where if it's even harder to compute the solution.
But now you don't need.
And yeah, you need, usually when it's p time, f is going to be locally Lipschitz, effectively locally Lipschitz, and thus the solution will be unique.
Is it a theorem?
It's a theorem, yes. If a real function is polynomial time computable, it has polynomial local modulus of continuity. I could write down explicitly what it means, but then it implies unicity.
Okay. What about some typical differential equations? I'm not sure.
So
Do they all fall into this category?
yes, yes. Any concrete differential equations is f is p time. Actually, f is more than p time usually. So for example, you say, well, maybe it's actually Lipschitz. That's a reasonable assumption. If f is Lipschitz, so if you know that, that's a strong assumption, but if you know that, actually it helps a lot. So then y is only p-space computable. So p-space, that means it could take exponential time, but at least it doesn't take too much space. So
Could you explain that with the lower bound, exactly meaning the lower bound?
So the lower bound is, can you find a counterexample like, can you find an example where y is really hard? So, for example, you could, like, if you only know the upper bounds, that means, okay, you know that if f is p times Lipschitz, then there's an algorithm to solve the problem in p space. But maybe the problem is simpler. Maybe you just don't have the best algorithm.
So by lower bound you mean there is no lower bound?
So here, lower bound.
That means NA. There isn't a.
Yeah, it means there's no better algorithm, basically.
On the show.
There's no, well, it's worst case complexity. That means there's no algorithm that's going to do better in all the cases. So it could be that if you, in most of the cases, you can do better. But this lower bound here, the thing that's p space hard, that's the same as the upper bound. That means there's no way you can do better in all the cases. It's like solving an NP-complete problem. Like there's no way to do better in general. But the definition of exactly what it means to be p space hard, given that y is real, is a bit technical. So let's just say it's hard. If you don't like Lipschitz, because it's a bit of a strong assumption, you could assume C1. And C1 actually also helps. Surprisingly, it helps the same as Lipschitz. And even more confusing, if you assume CK starting from k equals 2, there's actually a gap between the upper bound and the lower bound. So we know an algorithm to solve them in p-space, but we don't know examples where it's really p-space hard. We only know examples where it's ch hard. So ch is a complexity class between p-space and p. So you don't know it's the counting hierarchy. So it's hard, but less hard. Okay, so that's abstract nonsense here. Okay, we're really dealing into things that are out of space. Right? P-space computable functions are really hard. That can be really horrible. Do you know P-space? Do you want to know? Yeah, you know P-space. So, for example, that's solving SAT problems with quantifiers. P-space. So logical formulas with quantifiers. That's pretty important. And finally, if you really assume a lot on f, like p time plus analytic, then finally there's a p time algorithm to do it. So you really need special f for y to be easy to compute, at least in theory. But on the other hand, polynomials are analytic. So if you have a nonlinear differential equation, polynomial differential equation, in theory it's easy to compute.
Why do you have nothing?
So here it's because you could prove there's a p time lower bound, but it's actually very technical. What does it mean to have a p time lower bound? So I prefer to leave that space empty. If you want to remove this dash, there's actually a theorem that says if you have polynomial differential equations, you can simulate Turing machine with them. So that proves that you can do p time, but you cannot do, for example, linear time. That's not possible. You cannot do quadratic time. You cannot do any n to the k with fixed k. You really need polynomial, but with arbitrary degrees. Fixed for every equation, but that can depend on the equation. So for example, that means there exists a family of polynomial differential equations such that the solution has complexity n1, n2, n to the 3, n to the 4, and with arbitrary degrees.
And analytic where?
F everywhere. Analytic over Rn. Or it's, let's say Rn.
And neuromorphic is not okay?
I don't know.
Or the rational functions is not okay?
I don't know.
Okay.
No, it's unclear if it's possible. It's unclear because next to the singularity, things could be complicated in computational words. I don't know. But that's a good question. I'd like to know the answer actually, but I don't know.
So rational functions.
Okay. If you rewrite your rational function, if it's really rational, you can rewrite it as polynomial actually. It's really rational, in which case that would work if you know the solution exists. So if you know the solution doesn't go through any singularity, then yes. Indeed. But for meromorphic, I don't know. Yeah, I don't know. It might be results on this. I don't know. However, just a little bit of warning here.
But let's ask about the look again. So, and whose are these results? And are they old?
Some of them are old, some of them are recent. So there's different offers, and it's not just one single offer, so I didn't put the references.
Okay.
But yes.
Are they coming from CS people? Or
Yes.
Is it mostly CS?
Yeah, mostly CS people, mostly this community of computable analysis, where typically Weierhosch and co-authors, when they studied complexity of real functions, they were interested in what's the complexity of maximizing functions, what's the complexity of integrating function, and what's the complexity of solving differential equations, and thus they look at those problems. However, there's one thing which is hidden there, which is everything is done over compact sets, which means that it can be a bit deceiving because there's no contradiction between the fact that p time plus analytic is p time solution. However, you can build this particular differential equation, which is polynomial, has n variables, and the solution is a tower of exponential of height n. And this is indeed polynomial time computable over a compact domain because it's bounded. But intuitively, computing a tower of exponential cannot be easy computationally, just because of it would take so much time to write all the digits. Like if you think 2 to the 2 to the 2 to the n, it's a huge number. So those results are in fact a bit deceiving because they do everything over compact sets, so they have kind of the same problem as before. Like some of the constants of the problems are hidden. And this is why I say it's also non-uniform complexity. So you have this thing that for every f there's a y, but it doesn't tell you that the map from f to y is computable. So it's hiding some of the parameters of the problem into the constants of the problem. So those algorithms are correct, but they have the same problem that they hide the complexity. And this is why you have this example of the tower exponential. So it's only slightly better than the numerical analysis thing. If you want to do better, there's actually a theory about this, which is called uniform or operator complexity.
Wait, so you mentioned slightly better. Could you say what exactly is better?
It's better because now you really look closely at the complexity classes, and the algorithms are all correct, and all the constants, if you are willing to read the proofs, they're actually there. But they will tell you that basically they depend in some really complicated way in F. So it's slightly better, but it's not much better because they still hide the complexity in those constants. Those dependencies are not captured by the model because of the way the model is phrased. So that's this non-uniform complexity. So it's the difference between, for every f there's an algorithm, and there's an algorithm that maps f to the solution, which is a subtle issue, but it's actually very important for complexity. So it's like, for example, if you want to understand the difference, maybe. Let's say for every n, okay, there is an algorithm that writes 2 to the n. Okay, let's say it's a Turing machine. For every n, there exists an algorithm, a Turing machine that writes 2 to the n in constant time. Right? For every n, there's an algorithm. That's just the algorithm that prints all the numbers.
How can it be constant if 2 to the n has no constant length?
Well, that's the thing. For every n, there's an algorithm. So for every fixed n, there's indeed an algorithm that gets to the end in constant time.
Yeah, okay.
Okay, so it looks, in this example, it looks completely stupid because no one would think about writing this. But this is what we're writing here in more complex term. We're writing for every n, there's an algorithm that writes to the end in constant time. That's basically what we're saying. But what you really want to say, what we really meant by computing to the end is not this. What we meant is there's an algorithm that to each n, that for each n writes 2 to the n, but there's no way you can write it in constant time, okay? To write 2 to the n, you need at least linear time. You need to write n digits, so in linear time. Okay? And that's non-uniform complexity, and that's uniform complexity. It's the quantifiers are different. Here we're saying for every n there's an algorithm. Here we're saying there's an algorithm such that for every n. And here it looks completely trivial, but when you start doing things here and all those crazy things about real numbers, you can easily lose track about where quantifiers are and what is uniform, what is not. But at the end of the day, those results, they're like this. They're saying we can write 2 to the n in constant time. So, okay, but that's not what we're really interested in, okay? So that's the problem. Fundamentally, all those people, they're writing this. So if we really want to study complexity of the problem, we need to understand the algorithm that takes into account all the parameters. And so when I mean the map f to y, it's like here. This is my algorithm. That's what I care about. This is like for every f, there exists a y. Completely different. And so fortunately, recently, some people have studied, finally, this. The uniform, also called operator complexity. So here, now, we have to write complexity bounds, but they have to take into account, first of all, the dimension of the problem, and f, and its representation. So here, we really care about how we represent f, for example. And the problem is now, when you start caring about this, it's going to give a completely different picture. Like all I've said before, it's going to look like it was a lie. Why? Because, of course, if f is computable, then y is computable. As I said at the beginning, the map is computable. But if f is p-time and analytic, then the map is not polynomial time computable. In fact, it can have arbitrarily high complexity.
And what changed? Okay, because now we talk not about the. Okay.
So now we're not talking about this, we're talking about that. We care about.
Talk about different algorithm in some sense.
Yeah, it's a
different specification.
Yeah, it's a different specification. Now we really care about the algorithm that takes f and produces y, and not the fact that for every f there's a y. And so now the picture is completely different, because even if f is p-time and analytic, the solution can still have arbitrarily high complexity, because it can simulate Turing machine. So we can try to go further now, add more condition. Maybe polynomial will help. No, it doesn't help. Of course, you could go down to linear. Linear helps because now you can have an explicit formula. It's an exponential of a matrix. And I think you can do it in exponential time. But even there, I'm not sure.
Just to clarify, so if f is polynomial, wouldn't it imply that it's p-time?
Actually, yeah, yes, that's it.
Okay.
Well,
so last two are actually polynomial and linear.
Well, okay, so there's a subtlety about the coefficients, which is what kind of coefficients do you allow in the polynomials? For example, you could have a polynomial with a coefficient that's not computable in polynomial time.
Okay.
Which would be cheating, but in the wrong way. Like, obviously, when you write down a polynomial, you don't write crazy coefficients. Maybe you write pi, but pi is easily computable. But you don't want to write a coefficient that encodes like halting of the Turing machine. That's not interesting. So that's what I mean by p-time. It's There's no cheating on the coefficients.
Okay.
But it's also related to how exactly you represent the f. So,
So to recall, by your f you mean f. So f has constant coefficients. So it doesn't depend on t, correct?
no, they don't. So for the linear, that would be really constant coefficient. So actually, yeah, it's true that if you go down really low, like in linear, maybe you should start to care about how your coefficient depend on t or not. Maybe there's some intermediate between those two. Like you could care about linear differential equation, but the coefficients are polynomial in t. And actually, this has been studied, and they're very efficient algorithm for this class. So if you have something like I'm gonna write it here. You have x prime equals a of t x, where a is a polynomial in t, or maybe analytic in t. I think these are called definite functions. Definite. And they are efficient, I mean, as efficient as it can be algorithms for this class. And because this is very specific class, you can say a lot about what happens, about the singularities, about the efficiency of the algorithm. So yeah, I think this is the class for which most things are known. If you go higher than this, then things go crazy. And these actually have algorithms that are efficient in practice and theory. So this is nice. But not all equations are like this. No? So,
and what if you just have a single equation that is quadratic?
This I don't know. And I know that if you go to algebraic differential equations, then things are much more complicated. I don't know much about the case of one equation though. However, I know that you can rewrite some of the algebraic differential equations. If they're polynomial, you can rewrite them as ODES and vice versa. And sometimes preserve some of the properties, but sometimes you lose them as well. So it's not always a clear relationship between the two. But so what is clear though, from all those things which are quite confusing, there are many different results, is that unless you look at linear differential equations, it's impossible to predict the behavior of y looking at f. Because already for polynomial, the behavior can be arbitrarily complicated. So a very small summary is that it's quite confusing. Depending on how you look at things, you can get a completely different point of view. Practical methods, they are efficient, but they give no complexity bound. They don't even always give correctness bound. Non-uniform complexity, so these kind of things, is very misleading because it could give you the impression that things are actually easy when they're not. And uniform worst case complexity, everything looks hard except linear. But it's also misleading because it's also worst case complexity. Okay, most of the equations are not super hard either. So my feeling is we're kind of looking at a problem the wrong way. Maybe we just don't really know how we should measure the complexity of this problem. That's what I want to say. And I have one hope, one result that maybe hopes to not fall into one of those three classes, and that's what I want to talk about now, depending on how much time is left. And the idea is to be a little bit more subtle and go to something called parametrized complexity. So if you've never seen it before, it's going to be maybe confusing. I can give another example on the board. The idea is still to look at the same problem, so we're going to assume f is nice, so for example, polynomial. And we're going to give the complexity likely in the uniform case, so we care about d, we care about f. But now we're going to introduce another parameter that's going to depend on the solution. So this ki, y, is a reasonable parameter of y that's going to measure the complexity, but this parameter must not be known to the algorithm. So that means the algorithm only takes as an input f is going to run, give a correct result, and the runtime of the algorithm, in theory, you can show that it's related to something that's very specific to this solution, something that is interesting, but the algorithm doesn't know it. So let me give you an example, because it looks a bit like magic. Imagine that you didn't know anything about number theory. Okay, I give you, or very little, you know that every number has at least one divisor, which is not 1. Okay, you really don't know much. So I look at the following problem: given n, find, if any, a divisor of n which is not 1 or n. Okay? So you want to find a divisor of n if it exists, and if it doesn't exist, you want to say no, there's no other divisor. Okay? So what could you do? Well, there's a trivial way of doing it, just enumerate all the numbers between 1 and n. Okay? So solution, enumerate 1, 2, 3, up to n. It could be a bit smaller, enumerate prime numbers, but okay, fundamentally doesn't really help. And of course, you could say, okay, this works, but it's not interesting, because if I measure the complexity like this, what's going to be the complexity of this algorithm? Well, in the worst case scenario, you enumerate all the numbers up to n, so it's n. But there are numbers n for which the answer is going to be much faster, because maybe 2 is a divisor. So there's another way to measure complexity, which is to say, well, actually the complexity is some function of n, which is, for example, the smallest divisor bigger than 1. Okay? And now, what's interesting and strange about this is that the algorithm doesn't need to know what's the smallest divisor. But the running time of this algorithm, nevertheless, is bounded by this function, which is the smallest divisor of n. Does that make sense? Mm-hmm. So what we've done is that we've just refined the analysis. We've said, okay, maybe in the worst case scenario it's n, but actually there's some fine-grained notion. We can actually give a more interesting bound on the complexity. But you see that now this bound, it depends on n. There's nothing you can say about f of n in general except that it's less than n. So in the worst case scenario, you say, okay, all of this is less than n. But in many cases, it's going to be more interesting. That's the hope. Okay? So here, that's what we're doing. We want to make the complexity depends on f of y. So now y is the object we're trying to compute. But of course, it needs to be something reasonable. Okay? For number n, I could argue that the smallest divisor is maybe something interesting about n. But if you could always take f of n is the running time of the algorithm, right? That's not very interesting. So we need some parameter that is interesting. That's what I mean by reasonable. And obviously not known to the algorithm. The algorithm cannot use this to bound its running time. And the important difference between this and the textbook thing that we've done before, because you could say this is going to look a lot like what we've done at the beginning. The difference is the result is always correct. The algorithm is not allowed to return a bad result, and it insists again, it cannot know this parameter. Okay, this is not part of the input. Here, it doesn't know what's the smallest divisor of the number is. And one result that I've obtained is the following. So it's we need to make a strong assumption. We need to assume that now f is polynomial. So P is going to be a vector of multivariate polynomials. There's no cheating on the coefficients. Okay? And the theorem is the following. Assuming T is T for any, even if I is unbounded, okay, I is not compact, I is arbitrary, can compute y of t with n digits in time polynomial in some parameters of the input. So there's the degree p, there's the absolute value of the coefficient of p, and a parameter L, which is basically the length of the solution curve from 0 to t. So, picture is useful. I wanted to do it in 6Z, but you know. So what does it mean? It means that assuming you're in this case, and the solution is very simple, it goes in straight line, then what this theorem says is, okay, the main factor of the complexity of this algorithm is the distance between those points here. However, if your solution is very convoluted and instead of going in straight lines, it goes like this, then what matters is what the distance of this line is. And the bigger the distance, the longer the running time. And it doesn't matter what t is. So here you notice that t does not even appear in the complexity up there, except for this parameter. So what it tells you is that in fact, what p looks like is not very, it doesn't matter in fact. What matters is geometrically what the solution looks like. And that's what I meant by, based on f, you cannot really describe the behavior of y. Y could be really complicated, but geometrically what I think is pretty clear that this length is a good indication of how complicated the solution is.
What would happen in the next substitution, like just z is equal to y divided by 2?
So that's a good question. I want to talk about this at the end.
Okay.
So yeah, so this is not perfect, but it has some features that are still interesting. So in particular, this is invariant if you rescale the time. So if you substitute z of t equals y of alpha t, you're not changing the complexity because now you're trying to compute at t, which is alpha less. The length has not changed. So at least compared to the previous results, we have something which is invariant by time rescaling, but it's not invariant by space rescaling yet.
What's the meaning of raising to d?
D is the dimension of the problem.
What's the point of doing that?
It's what I mean by this is that the polynomial here does not depend on anything. It's a fixed polynomial, but it has to be raised to the d. So for example, it's what I mean by that is, for example, maybe the complexity is something like I don't know, n times log.
Does it actually mean that complexity in d is exponential?
Yeah.
Okay.
So for example, this, if you had this expression, then the way I would write it is, okay, this 2 doesn't matter. It's a constant of the algorithm, so it's a polynomial in n L y t. But then you still need to raise it to the d. Okay, so it's exponential in d, but otherwise it's polynomial in all the other parameters.
Does this result also tell you how big the coefficients are of this polynomial?
It depends on the parameters of the coefficients of p, yes.
Right, but
You mean of the coefficients of y?
It's polynomial time, right? So that's what you're saying.
Yeah.
So it's some polynomial. What are the coefficients of this polynomial?
You mean p? Or
I think I actually asked whether this polynomial you can write explicitly.
the coefficient. Okay, sorry, I didn't.
Yes.
No, I don't know. I don't really know what it is. I mean, if you went to the proof and really care about it, you could get it, but it would be so horrible. The thing is, I don't want to know. I don't want to know what it is.
Want to know.
I don't want to know.
At this point, maybe the next time you'll be.
Maybe. The thing is, it's horrible. So first of all, the way the proof is written, it relies on a sub-algorithm to compute like Taylor approximations. And so they're very good algorithms to compute Taylor approximations over these. But they're really complicated to implement as well. So depending on that, this is a parameter of this polynomial, okay? And the second thing is I do a lot of like upper bounds just to make things slightly simpler for the analysis. And if you went there and wanted things to be like you really wanted to be careful, you could obtain something better. But then this polynomial would be so horrible, I just don't know. I want to write it down.
Right, but you criticized others for hiding.
Yeah. But this polynomial though, it does not depend on anything. It's a constant polynomial, fixed once for all. It does not depend on any parameter of the problem. It does not depend on p, it does not depend on n, it does not depend on anything. It's like...
But I still don't know it, so what's the...
You still don't know it, but well, you could find it if you... But the thing is, I've tried to... I don't know if do I have the slide? No. I've actually tried to implement the algorithm. But you don't want to use it, it's just way too slow.
And what's the point of proving such as...
So the point, I think, is to show that maybe the proper way of looking at the complexity of ODES is to introduce parameters about which you care, and parameters that try to measure how complicated Y really is. And I think the length is one such parameter. It's not the best, but it's maybe one step better than just all the previous results that don't tell you anything. But the problem is, this result is so theoretical that it doesn't really, in practice, give anything for now.
Do you hope that there will be something in practice related to this?
I think, one day, yes, it might be, I think so, yeah. I have one slide though. I think it gives some insight about why some method work and work more or less better. If I still have time and you're still interested. I don't know how much time I have left. Not much?
Maybe we shouldn't ask.
Okay, so I'll just skip some things because those are not very interesting. That's how the algorithm works. So I'll still say one thing which I think is interesting. So there are lots of myths about this thing that called the order of the methods. So I've said at the beginning, like those numerical methods, they're order 4, order 3. There are lots of things about, order 4 is the best, implicit method of order n, and like explicit method of order n plus 1. There's pseudo-theorems about you cannot do things, blah, blah. So one thing that the algorithm gives is an explicit complexity bound for any Taylor algorithm of order omega. So if any Taylor algorithm that you could write, it's a particular case of this algorithm in some sense. And so this is what the complexity of an algorithm looks like. It's a big O, which is a real big O, by the way, of L to this power epsilon times this. So epsilon is the precision you hope for, and L is the length of the curve. So L is this thing. Okay? So what's interesting now is if you take some particular values of omega, you can recover things.
What's the meaning of approximately equal?
It's because there's this the coefficients of p that are introduced. So in fact here it's like there's a constant here that depends on the coefficients of p.
Okay.
In fact I lied a little bit. It's not really the length. It's some integral that you can relate to the length. But there are degenerate cases, like if you have an equation where the derivative can become arbitrarily small, so your system almost converges in finite time, then this analysis breaks down. So, for example, if your system was something like this, you start from y0, and the solution converges to a point. Okay, the length is bounded. But computing this fixed point, you cannot do it in constant time. So this is where this method breaks down. This thing is relative to the length if your derivative is always bigger than say 1, for example.
That's the why I take max.
Yeah, that's why I take the max. So it's a technical defect of the method. Okay, and if I would like to get rid of this, But if I don't get rid of this, that means my method would imply an upper bound on computing the fixed points of the differential equation, which is a non-trivial thing.
What is not real? I mean, it's just a polynomial system. Like you set all the units to be 0 and then solve polynomial system, isn't it?
Yeah, you just have to solve a polynomial system. That's
So you consider this? Okay.
yeah, I mean, yeah, you can do it, but it's not.
Yeah, so you were talking about like arbitrary computable functions, and compared to that, I just had an impression that
that would imply an upper bound on computing the zeros of a system of polynomials. So it's you can give such upper bounds, but they're not trivial. So
yeah, but like they're also exponential in dimension.
Yes.
So it's not impossible.
It's not impossible. Yes. I just it's a side remark that it would imply this. So,
okay.
So that's.
So it's kind of indication why it's hard to prove.
Yeah, I think that's an indication of why I think it's hard to prove. So, for example, what does this bound means? It means that if you take Euler's method, then Euler's method has complexity L cubed divided by epsilon, which explains why it's so horrible. Because if you take epsilon equals, I don't know, 10 to the minus 4, which is like pretty typical, you want 4 digits, then this is like L cubed multiplied by 10 to the 4. So it's a pretty big number for L, which is like not like significant.
But like if you don't know big O is.
Now the big O is just it's an actual constant. It doesn't depend on any parameter of the problem. This is just to give an overview. Now the thing is funny, which is if you increase the order just a little bit less, like by 1, it's not much, then already you go from cubed to square, and you square. You take the square root of the epsilon, which means that for concrete examples, the difference between these two bounds is actually huge. It's almost, the first bound is almost squared of the second, which explains why the difference between Euler's method and a method of order 2 is huge. For concrete examples, this Euler's will not work, whereas the other will work. And if you take just one order more, it's again almost you take the square root of the bound. Which means for small orders, very quickly you can increase your complexity by just doing one order more, and you don't pay much more computationally speaking. And if you're smart, and you take the order at exactly the right level, which is 1 plus this log, assuming you know the length, but you don't know it, okay? But assuming you know the length, you could obtain something which doesn't depend on epsilon anymore. But of course, this is number of steps. So each step, computationally speaking, it takes some time that depends on epsilon. Okay, this is number of steps. It's not the overall complexity. And now, assuming you could do Taylor with infinitely many terms, okay, assuming you had this power, which you can't, but assuming you could, then in fact you couldn't do much better than this. It would not really help you. And what the algorithm does, what we do, is something a bit smarter. We actually change the order at every step, and it's the same as Taylor if you had infinitely many terms. So what it means is that if you stick to Taylor, so explicit methods, this is basically the best you can hope for. And the strange thing is that the number of steps you can make it so that it doesn't depend on the precision. And it also explains why at very small order you can win a lot by increasing. But starting from order like say 4 or 5, it makes less and less sense because you pay a lot more to gain very little in the accuracy.
I'm a little confused. So before you had complexity like L to the D, and now you have big O of L.
That's the number of steps. It's not the overall complexity. So the
how is it related to
the overall complexity will be like number of steps times the cost of each step. Okay.
So, but does the cost of the step depend on?
It depends on Taylor, basically. It's a Taylor expansion of order omega, and you need to precision epsilon.
So when you decrease number of steps, you can actually increase cost of each step. So it's
You could. It's a trade-off which is not trivial to make. Actually, in general, it's a completely open question as to what's the optimal trade-off. So I could say more, but I think I've already talked a lot. So, but yeah, there's a trade-off between the two. However, you cannot make the number of steps arbitrarily small, because at every step you're doing a Taylor expansion, and you can't do less than the radius of convergence in terms of steps. Okay, if your Taylor expansion only works for radius 1, then you cannot do a step of size less than 1. Doesn't make sense. So this is like, there's a lower bound to this number anyway. However, the max order shows that here it doesn't make sense to take order arbitrarily high. I mean, not that it was really surprising, but yeah. So yeah, to conclude, things are quite confusing, I think. So solving numerical differential equation numerically, basically they're vastly different algorithms and results depending on what you expect. So if you just want a practical algorithm, you can use those results in the literature that give you no complexity, but sometimes correct results, sometimes not. There's all these things about non-uniform, uniform complexity, which is very misleading, and on top of that is very pessimistic. Then there's this result about uniform parametrized complexity with the length, which I think is encouraging, because it's a polynomial time algorithm. So that means that at least we've recovered the fact that it's polynomial. But now we just have this parameter. So I'd like to know what we can do with this parametrized complexity. Can we say more? Can you bring insight to practice? And this thing about geometric complexity, so have you mentioned? So this is, the length is invariant by this kind of rescaling. But if I do other rescalings like, even simpler than that, you take the equation and you say z of t equals y of t minus any number. Like say, okay, I shift everything by y0.
But it doesn't change length.
It doesn't change the length, but it changes the coefficients of the equation. And my polynomial still depends on the coefficients of p, unfortunately. And the coefficients of p is not something geometric. And on top of that, as you said, if you take z of t equals like the half of y of t, then the length decreases by 2. But should the complexity really decrease by 2? It's unclear. Because you would say, okay, the equation hasn't changed. Is it really much easier to solve? But in some sense, yes, because the numbers are twice smaller. So asking for 1 digit more is easier. Like if before you were asking for 3 digits and you divide everything by 10, then in fact you just need 2 digits now. If you scale everything to 0, then the answer is trivial. You just output 0. Everything is 0. So it's very easy. So it's not clear how it should depend on spatial rescaling. Okay. Or at least it's more subtle. You would need to increase the accuracy of what you need. So there's some kind of trade-off. It's more like, it should be like length times 1 over epsilon, for example. Like there's a trade-off between the two. So it's not as simple as it looks, I think, unfortunately.
Okay.
And on top of that, I think the length is still not the optimal measure because intuitively there's still a difference between something which is like straight but long. So imagine you had something like that. So L is like very, very big, but the equation is almost straight. For example, linear equation or constant equation. And something which would be like that. So maybe y of t is very close, but the equation is doing something like very complicated like this, oscillating really, really fast. And maybe at the end, those two equations, they have the same L. But this one still seems harder to simulate because it's making so many oscillations. It's not, with the Taylor method, there's no way you can do this efficiently. At least it doesn't seem so, because Taylor will never give you like oscillation like this. You'll have to do 1 per oscillation. Well, a straight line, in theory, you could do 1 step, 1 big step. So the length is not the end of the day. It's like it's something. There should be something more precise. I think more precise parameter. Something like maybe the sensitivity to the initial condition is quite important.
So, but maybe like when you can include, when it can compute length not in the space with y coordinates, but the space of y and y prime coordinates or something like that. So it's
Yeah, maybe that's. I think that's the interesting thing. Like it opens up the like Pandora's box. Now you can think about all kinds of parameters that are maybe more interesting for some problems and for others. So yeah, I think it's now there's just no limit to what you can think about. Other questions? There were many questions already.
yeah, thank you.